Hello team, welcome to part 2 of our look at transformations of graphs. To summarise, we can have a look at what we've already done in part 1. In part 1 we defined transformations in both coordinate and function form. Algebraically, we looked at translations, dilations and reflections, and we started applying them to functions. What we're going to do now though is look at combinations of all of these. Okay, so prior we were only applying one type of transformation. Now we're going to look at applying multiple of them, and then we will also look at identifying transformations that have applied to a function. So in that case, you'll actually be told f of x and g of x, and we've got to figure out what were the transformations applied on the way across. So let's jump straight into it. So combined transformations, we can realize that for each coordinate point, our x or y coordinate, we can apply multiple things to it. We can apply a dilation or a reflection. So this is a dilation and reflection. And we can also apply a translation. And the same goes for the y coordinate. So we can apply all of those to either point or all together. Out of that, if, and this is where it gets a little bit tricky trying to use inspection or the function form of transformations, if they've been applied in this order here, where dilation or reflection, these two can sort of go together, but then translation afterwards, so this like Dr. T and mnemonic to remember, if they've been applied dilation, reflection, then translation, it can be represented in this form. If not, if it's being represented in a different form, we might have brackets around like this, or it might be inside, it might be f of x on b, then minus h, depending on the order that those have been applied in. But if it's dilation, reflection, then translation, it can be represented as it is written there. Saying that, as long as you remember our replacement shortcuts, then the order, remembering this whole big fancy write out isn't critical. As long as you just apply the replacements in the order that you're told to do them, then that's completely fine. So let's jump straight into it and look at a combination. First, just building, let's build this in coordinate form. So reflection in the x-axis, followed by a dilation factor of factor 3 from the y-axis. So we've got a dilation of factor 3, we've got a reflection in the x-axis, followed by translation 2 units in the negative direction of the x-axis, and 4 units in the positive direction of the y-axis. So we've got 4 transformations there. So let's apply them in order. We're going to go 1, 2, and then 3 and 4 together here. We'll do both translations there. So let's apply the first one, just working in order and following what would happen intuitively to the coordinate. If we reflect in the x-axis, we're doing that. So the y coordinates are actually made to the negative versions of themselves. So this would become x negative y. And so that's the first one done. One is done. Second transformation, a dilation of factor 3 from the y-axis. So we then multiply by 3. So our x coordinates are being multiplied by 3. So it's going to turn into 3x, and we still have our negative y. So that's our second one done. Okay. And then we've got to translate 2 units in the negative direction of the x-axis. So we are moving everything minus 2 this way. So our 3x is then having 2 subtracted from it. And our y-coordinate, 4 units in the positive direction of the y-axis. So our negative y is then having 4 added to it. So now that we've applied all those, we can see our x dash y dash would be equal to 3x minus 2 and negative y plus 4. So that's our new coordinate point relative to our old coordinate points. So it's just applying them in order that they're stated using common sense. Okay, what is happening to that coordinate point as you do that transformation? You don't need to worry about the whole graph, just think about an individual point, what would happen to it. let's move on then. What's the next step from there? Well, the next step from there would be, if you've got something like this, well, then we apply the rest of the process the same. So that's what it's just saying here, is once we've found our rule for our series of transformations, let's just apply it as we have in previous sections. So here's a new problem. Okay, it's a different one from this prior one. We've got an actual equation now. In this prior one, we didn't even have an equation. It was just find what's the coordinate notation for the transformation. Here we know it's y equals square root of x, and we are reflecting in the y-axis, followed by translation 3 units in the positive direction of the y-axis. So there's only two transformations, but it's still a combination. And we can see the negative x, and then we add the 3. So this is our coordinate transformation. So all we do is follow the rest of our steps from video part 1, where we rearrange, we equate our coordinates. So the x dash is equal to the negative x, and the y dash is equal to the y plus 3. We rearrange to get the original x and y by themselves using inverse operations. So we're left with negative x dash, and y would be equal to y dash take 3. So we're just rearranging. And then we substitute those into what was the original function back up here. So where y was, we're going to put y dash take 3, and where x was, we're now putting negative x dash. From there, if you then make y dash the subject, we get our rule, and then we want to write it, let's call it g of x. And there we are. So our new function that's transformed from the original one is the square root of negative x plus 3. And that should be nothing really new there on this slide. Okay, the bits here, okay, that's nothing new. Just equate the coordinate pairs, rearrange to get the original x and y by themselves, use those equations, substitute into the original equation, and we get our transformed form. The only new bit is making this, just applying first transformation, then second transformation. Just do them in order. If we want to do that same problem with inspection, or our function form, it's just by looking at the equation going, okay, what happens? If we reflect in the y-axis, we know that we replace x with negative x, and that's what we're told to do first. So we do that replacement first. We get that. So we've started with y equals square root x, replace x with negative x, and then from there, if we translate 3 units in the y-axis, we replace f of x with f of x plus 3, or you could think about we just stick plus 3 on the end. So we've put plus 3 on the end, and we get the same equation. So again, nothing's changed from part 1 video. Just identify what is the shortcut for that transformation and then apply those in order. If you are using the inspection method, okay, just got to be careful, as we talked about in the part 1 video, that if some of those shortcuts like this one, replace x with negative x, that you're doing it explicitly to the x and not something further outside. Okay, so let's have a look at an example of that. Using function notation inspection, write down the equation of the image when the graph y is equal to x squared plus 1 is transformed by a dilation factor of 3 from the y-axis, so we have that transformation, followed by a translation of 2 units in the negative direction of the x-axis, followed by a dilation of factor 5 from the x-axis. So you can see in that prior slide we talked about Dr. T, dilation, reflection, then translation. Clearly this problem is telling us not to go in that form, so we just got to be really careful that as we apply things, we follow our shortcut rules. So we have y is equal to x squared plus 1, and our first thing is a dilation of factor 3 from the y-axis. So if we're dilating from the y-axis, we're being stretched this way. So that means, let me put a 1 there, we need to replace x with x on, in this case, 3. That would be our replacement strategy, that if we remember the rule. So let's do that. So we get y equals, and the correct way to do this is we have to replace the x that is being squared. Some people, so that's correct, people make the mistake of going, oh, it's the x squared, we need to divide by 3, and then the plus 1. And this here, that's incorrect. We're replacing the x itself, not the x squared. You have to replace the x itself with whatever operations are being applied to it after the replacement that you're putting in. So that's our first one. Let's look at our second one, a translation of 2 units in the negative direction of the x-axis. So that's our second one. So the second we need to replace, and again we need to replace x with, and in this case it's the negative direction, 2 units x-axis, so we're going to replace x with x plus 2. We swap the sign when we're moving in the x-axis direction, so we're now going to get y is equal to x plus 2 all on 3 squared plus 1. And then we can finally look at our third one. Okay, dilation of factor 5 from the x-axis. So that's our third one. So we're dilating from the x-axis, so we're stretching up here. Okay, so the third one is we need to replace f of x with, and in this case it's going to be 3. It was no dilation factor of 5. f5 f of x. Okay, so the whole of fx needs to be multiplied by 5. So in this case, we're going to get y is equal to 5 x plus 2 on 3 all squared plus 1. Now, I've put these extra set of brackets in. Let me put them in red so we can see. That's really important because the 5 needs to be multiplied by everything. It's 5 multiplied by f of x, and currently f of x is what's in the red brackets. So we could then expand that out to simplify this a little bit. This could also be rewritten as 5 x plus 2 on 3 all squared plus 5. These two graphs would be equivalent. So that's how we use inspection and make sure we only apply it to an x. Just follow the order that you're told to do the translations in, and you will have the final form. Right, we're on to the other bit of the learning intention for this video, which is determining transformations. So as I said, determining transformations is we are told our first function and we are told what the new function is, and we need to figure out what has gone on to go between those. So let's have a look how we can do that in coordinate notation. What you need to do is this step here. It's very simply stated as rearrange function 2. So we call this our new function. It's got the dashes in it. And let's call this our old function. You got to rearrange function 2 into the form of function 1. Now, what does that mean? Well, that means that based on the operators in function 1, you need to rearrange the other one. So all operators are done directly to the x or y variables before anything of the form of function 1. So what I mean by that is if we look over here, we can see we have the x dash plus 1 all cubed. So the x dash is having 1 added to it before it gets cubed. Before this cube happens, that's in the original form. So that's fine. That bit there is fine because the plus 1 is being done to the x before the cube from the original form. But after the cube, if you follow BIDMAS, you would then do the times by 3 and the minus 5. Those operations, the times by 3 and the subtract 5, are being done to the function after this original cube operator, and we can't allow that. So what we need to do is, and we can rearrange that by taking things, as you can see in this working out here. Okay, this is rearranged to effectively a similar form of y equals x cubed. Okay. And we can see the plus 5 is being to y dash, the 3 divided by 3 is being done directly to the y dash, and there's nothing being done outside this like cube or the brackets. That's what we have to avoid and what we mean by the form of function 1. Okay. From here, we work backwards. If we think of what we did here, in this problem we have this form. What we can do is we can equate our coordinates or our variables in reverse. So if we write technically the functions, let's write them above each other, y equals x cubed, and we have also y dash plus 5 on 3 equals x dash plus 1 cubed, we can now quite, and this is, we can see that form a little bit more. This bit is equivalent to that bit, and that bit there is equivalent to that bit there. If we had anything over here, you'd be going, no, that's not equivalent because the cube gets in the way. So that's why we're moving things out of away from that bracket or that right-hand side of the equation, because we can't identify the equivalents there. So once we've identified those equivalents, we can write out this equation. We get these two equations, y is equal to y dash plus 5 on 3, and x is equal to x dash plus 1. And if we keep going, what we want to do is rearrange them to actually get x dash and y dash by themselves. So this is reverse. Because we're effectively doing the whole process in reverse, we want to reverse because we want to know, well, what's the new coordinates relative to the old ones? And once we rearrange these two equations and get y dash and x dash by themselves, we can see that y dash is equal to 3y minus 5 and x dash is equal to x minus 1. So we can write now our transformation coordinate form, x dash comma y dash. We can write that, well, the original x and y, x is subtracted 1, 3y minus 5. And we just then read off, well, what's happening to the coordinate? Well, x coordinate has 1 subtracted from it, so that means it's translated left. Okay, and then the y coordinate, okay, is times by 3, so we've got a dilation of 3. Okay, and then it's also translated 5 units in direction of the negative y-axis. Okay. The order here is written a little different to what I just read them out, but what you do is just effectively read each of these in BIDMAS order of operations order, and you could, and this one jumps between, it does the dilation of 3 and then it goes back and does this translation and then comes back and does this translation. But I personally just look at the one coordinate, so the x coordinate, and I go, okay, that one's translated left 1, and then I look at the y coordinate and go, okay, then I list all those transformations. It's translated, dilated by 3, I should say, and then translated down by 5. Well, that's how we go about it. If there was brackets in here, like it's mentioning here, well, then that changes the order that you would have to mention them. If the bracket was there, the y minus 5, you would have to mention that translation before the dilation of the 3. Okay, so when you're stating them, just focus on that one, then focus on that one, and then write them off. There we go. This is where inspection starts to become a lot harder. Okay. You have to be able to pull this off with inspection and identify the transformations, is know what the replacement rules off by the top of your head, and then think of what would be the replacements that would get you from the original function to the new function and make it look as this new function is. So for example, we're starting with, and this is where the order of those replacements becomes really critical, and this is when people most make mistakes. So we're starting with y equals x cubed, and we're ending up with this form. Okay. This shown is in the correct order, and the next slide will show if it's in the incorrect order. So if we dilate by 3, okay, so in this case, we've done 3f of x. Okay, dilation of 3 from the x-axis, that's the first replacement, and that's how we can get our 3 there. Okay. From that, since now the 3 is there, we can put in our translation. Okay. So translate of 1 unit in the negative direction of the x-axis. So this is where we are replacing x with x plus 1. And that gets us our x plus 1 in, so our 3 is in, our x plus 1 is, and then we need to get subtract 5, so we want to translate 5 units in the negative direction of the y-axis. We want minus 5 in the end, so this is where we replace f of x with f of x minus 5, which is that translation. If we look at something, if we did it in the wrong order, okay, and I'm going to scrub that out, I'm going to put it there. If we try to apply this translation first in the y-axis before the dilation of 3 from the x-axis, which technically impacts the y-coordinate because you're stretching it up and down. If you translate it up and down and then stretch up and down, those compound on each other. So if we put the translation in first, okay, that's fine, the minus 5 goes in. We put the horizontal translation in, okay, we put the plus 1 in, that's fine. But if we do a dilation factor of 3 from the x-axis, that's where we replace f of x with 3 f of x. That's fine, okay, we got our 3 in there. But that has to be applied to everything, which technically means it's going to be applied to the minus 5. If you then expand that out, that becomes negative 15, and that does not match. That does not match. Normally the best way to go about this is to do the DRT. To avoid making mistakes, apply your dilations and reflections first, then apply your translations. That 99% of the time, unless it is written in an odd form, unless our final function is written in an odd form, sort of like this with brackets in there, you'll get the correct order. You'll get the correct order. Some of you, and this is an extension thing, so if you're already cognitively loaded, that's completely fine. But if you're grasping this, some of you might notice and go, oh, technically, doesn't that mean back here, if I had have put a translation of 5 on 3 instead, if I made that 5 on 3, 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 when I multiply the 3 through, this actually becomes 5. And that is fine. And yes, that is correct. Okay. There is technically an infinite amount of ways to go from your original function to this function here. And that will almost always be the case. You could translate right by 2, but then translate back left by 3 to get a total of a minus 1 translation to the left. And then you could dilate by a factor of a half, then dilate by a factor of 10, and those two come back to be a dilation factor of 5, and then somehow you could turn it into a 3. You're adding more steps, but technically there is an infinite amount of ways to go from one to the other. What we're looking for is a simple list that would be, if in the order that you've written, does work. If the list you write, if we apply and I'm marking and I check and I apply it and it gets the final function, well then that's fine. Okay? And like I said, 99% of the time, if you're using inspection, you follow the DRT. Okay? Using inspection to try and figure out, let's apply dilations first, experiment with them, then apply reflections, then apply translations to get your final function that you've been told. That's okay, and that'll get you there. Otherwise, you can always fall back to your dash method, and that's why we teach both ways, is that applying transformations with inspection, if you remember the rules, is very quick, but identifying transformations, much harder. That brings us to the end of transformations of graphs. Okay. Part 1, we did this, tick, and we did some of this. We have since come back now, part 2, and combined these and applied, and we have also identified transformations applied to a function when we're told f of x, and it's gone into some g of x, and we've figured out what is there. As always, if you have any questions, put them below in the comments or on Google Classroom, and have a good day.